All right, so the first of our assumptions is that the expectation of u equals 0. So I use this random variable as just saying the expectation of it equals 0. Well, it's not really a big assumption we're making. I mean, we could always kind of make this true, right? We could subtract the mean. We could always standardize some random variable so it has a mean of 0. So this is not really a big assumption. Can always make this true. So not a huge assumption there. It's just a really simple assumption about these unobservables. But this second assumption, expectation of u given x equals 0, is a much stronger assumption. And what it's saying is that the average value, hopefully you can read that, of u does not depend on x, does not depend on x. Another way to put that is u is mean independent of x. Okay, I mean, is this assumption likely to hold? Well, in kind of our simple regression, we kind of gave this really kind of simple example, right? Where maybe we had wages equal beta 0 plus beta 1, maybe years of education plus u. And everything else besides education that affects wages is in this u. So things like experience, ability, everything. And so what this assumption is saying is that the average value of these things is independent of the average value of education. It's probably not going to hold in a situation like this, right? I mean, maybe there's a positive relationship or correlation between ability and education. So some kind of scholastic ability or whatever, and education, maybe there's a positive relationship. That would screw up this assumption. So this is a big, big, big assumption we're making right now. All right, so we have our simple regression model here that we wrote out before. So remember, y is that independent variable. The example we were doing is wages. Beta 0 and beta 1 are parameters. These are the true values of the parameters. You know, this is probably something we're never going to know, but we want to learn about. That's what our goal is, to use an estimator to learn about these things, or estimators. X1 is that dependent variable. So the example we were given was education, or years of education, and u was that disturbance of the error term, where everything else besides this x1, everything else that affects y is kind of in there. All right, so let's take expectations of both sides. Sides with respect to x. So we're taking the expectations with respect to x. So the expectation of y given x, and we're taking the expectation of beta 0 given x plus the expectation of beta 1 x1, and I should say x1 here to be correct, I guess, and then plus that expectation of u given x. So a couple things. This is a constant. So is this. They have actual value. These are the true values. We're never going to probably know it, right? But there is a true effect of education on wages. Might be really hard for us to learn a lot about it, but there is a true effect, and that's this true effect here. So it's a constant, right? It's not a random variable, so we can use those rules of expectations. And again here, we're taking the expectation of x1 with respect to x1, which is just x1. And finally here is this assumption. Remember, this is that, we made an assumption that this equals 0 just a couple minutes ago. So what does that mean? Well, if we use those kind of rules, we have the expectation of y given x1 equals beta 0 plus beta 1 x1. Again, the expectation can go through everything because beta 1's a constant. The expectation of x1 with respect to itself is just itself. And this is equal to 0. We're going to call this PRF, which stands for population regression function. And so, I mean, what this is saying is it's relating, and it tells us the average value, tells us how the average value of y changes with x. So how, for instance, wages change with different values of education. It's not saying that everyone in the population, if you have 10 years of education, is going to have this exact amount. But it's giving you the average wage at a certain education level. So let's take graphically, let's kind of draw this out and kind of think our way through this. Okay, so the population regression function was the expectation of y with respect to x1 equals beta 0 plus beta 1 x1. So let's graphically draw out this relationship. So we have y on the y-axis, so you can think of wages, for instance, education on the x-axis, or just some other variable, whatever one we want for x. And it's basically saying we have this linear relationship, right? Where the slope is beta 1, the intercept is beta 0. It's kind of relating the average value. So this is exactly what this is. Kind of relating the average value of y with different levels of x. So for instance, let's get a different color. I don't think green and blue are different enough to maybe see it. So it's kind of telling you is like, so some value of x, this is the average value of y given that level of x. But it doesn't mean everyone is along this line. It just tells us like the middle of that distribution of points. Can't draw 3D very well, 3 dimensions very well, but there's a distribution of people maybe around these different levels, this certain level of education. It doesn't say everyone's on this line here, just saying the average of all the people with this many years of education is at this point here. So we have these kind of distributions of points. So even there's, this is the population regression function, and it's like the true values of, the return on education and whatever beta 0 is. It doesn't mean that everyone's along this line. It's just saying the average value of y given this level of x is some value. But there's still a distribution of different points around there. Okay.